define system software in many ways. So it is going to support the operation of the computer. It is the one way of defining the system software. Another way is it is going to act as an interface between the OS and as well as the users. That is the second definition we can give. Okay. So just now I told you, when we have this system software, the system software is depending upon the machine. That means it depends upon the architecture. So when we want to implement a system software, we have to look into the architecture of the machine. So architecture in the sense hardware features. So these common hardware features are defined in SIC machine. SIC stands for Simplified Instructional Computer. Simplified Instructional Computer. Okay. It is going to have the hardware features that we can find in the real machines. So two versions of SIC are, first one is SIC itself, the standard model. Another version of this SIC is SIC/XC. So the SIC/XC here, the XC stands for extra equipment. Okay, so now we'll go with the first one, SIC. So in the previous class you have studied that when we want to implement a system software, we have to think about the memory. So what is the common memory it is required here is 2 to the power of 15 bytes of memory is required. Okay. So what is the size of the memory which is supported in SIC machine here is 2 to the power of 15 bytes of memory is required. And we know that 8 bits are going to form a 1 byte. So like that, 3 consecutive bytes are going to form a 1 word. Okay, in the previous class I have explained what do you mean by consecutive bytes. That means bytes will be in a one row. Each row will be having 3 bytes. So that memory location. So size of that memory location will be 24 bits. Okay, so 3 consecutive bytes are going to form a one word. Word in the sense each memory location. Size of each memory location. Next, this SIC machine is having registers. So it is having 5 registers and each register is of size 24 bit. So in the previous class I have explained all this, just I will recall. So the first register is A. Mnemonic you have to use A for the accumulator. Or you can specify this accumulator register with the integer number as 0. So this accumulator is used for arithmetic operations. In the previous class itself I told you how to use this. That means if I write a instruction like this, this Word document I will keep and I will explain. Okay, so you are having a general purpose registers also. I told you, no, in the yesterday's class I have displayed this one. You have registers R1, R2 and R3. I hope this is visible. So you have registers R1, R2 and R3. That is, this is the internal architecture of the processor. Here you have an accumulator ACC. Okay, so when we use this ACC, if I write an instruction like this in assembly level language, add R1. So what it is going to do? It's going to add the contents of R1. I'm repeating, it's going to add the contents of R1 with the accumulator content. Assume that in the accumulator you have 10 and in the R1 you have 20. So both will get added and the result will be stored onto the accumulator back. Okay, so accumulator will be used internally by the processor to store the results temporarily. Okay. Next we have this X. Why X is used? Yes, why X is used? X stands for respond Madi.
Index register.
Why it is used?
Addressing.
It is used for addressing. Okay, but when it is used, when we use index, when we want to access the array elements, right? How do we access array elements? How we access by taking an index, right? So when we are going to use the index, at that time this x register is used. You will understand once you write a simple programs. You will understand why we have to use this A register, X register. Then what is L? L stands for
link register.
why no girls are responding? Only one or two boys are responding. Why it is used? Linkage register. What is the example I have given in the last class? It is used for storing the return address. What do you mean by return address here? When we use this JSUB instruction, right? When we use this JSUB instruction, say I have this JSUB instruction. JSUB in the sense jump to subroutine. What is the subroutine? F1. C language only just you will specify F1 with a semicolon, right? Indicating that you are calling the function F1. But in assembly level language we are going to use. So when we use assembly level language, the instruction JSUB is used. Jump to subroutine. What is the subroutine name we are using? F1. So assume that this JSUB instruction is at the memory location 100. Okay. So when this function is called, F1 function is called from the main function. So the control will be given to the F1 function, right? The control will be given to the F1 function. So once all the instructions are executed from the F1 function, the control has to be given back to this main function and it has to continue with this instruction int A. It is present at the memory location 104. That means it has to continue with the next instruction what we have after the JSUB. So we have to store this 104 as the return address so that once after finishing the execution of the F1 function, the control or it will resume from this int A instruction which is there after the JSUB instruction. So in order to keep track of that, this return address 104 will be stored in the linkage register. Understood? Hello.
Yes, ma'am.
Now I will ask you a simple question. What about this one? Assume that we have a F1. F1 is calling F2 function. F1 is calling F2 function. Now assume that this F2 function is at the okay. Now assume that this F2 function is at the memory location 300. Okay. So here somewhere you have defined F1, F2 also. Second, I will take it. Now assume that F1 is calling the F2 function. Okay, now see, main function is calling the F1 function. So the control will be given to the F1 function. In the linkage register, you will be having the address as 104. Okay. Who is that? Anybody wants to join? Okay. So assume you are having a main function. In the main function, you are calling this F1 function. So the control will be going to the F1 function. In the linkage register, what will be the address which is stored?
104.
104. Okay. Now assume that control is coming here to the F1 function. Okay. F1 function, control is coming to F1 function. Now assume that F1 is calling F2 function. So now what will be the address we will be having in the linkage register? One ನಿಮಿಷ ಇನ್ನು ಈಸಿಯಾಗಿ ಅರ್ಥ ಆಗಬೇಕು. So I will give you. After F1, you take some instruction. Now you people tell me, So here the F1 function is called. So the return address will be 104 in the linkage register. Okay. Now come to F1. F1, assume that it is executing the int instruction. Okay. But now assume that F2 function is called. Okay. Now F2 function is called. After returning from the F2 function, it has to continue with the instruction which is at the memory location. 212. Okay. So what will be the contents we will be having in the linkage register? F2 is calling, F1 is calling the F2 function, right? After execution from the F2 function, after returning from the F2 function, it has to continue with the instruction which is at the memory location 212. But what was the initial contents of the linkage register?
104.
Now it will be overwritten. No. Why? Because F1 is calling F2 function. So now after returning from the F2 function, it has to continue with the instruction which is at the memory location 212. So now we can say that linkage register contents are getting overwritten. So what at that time we say that this 104 is getting erased from the linkage register. So there will be no track that from which function it has to resume. So for that purpose, what they will do when we have functions like this, when we have nested functions, they are going to make use of the stack. Understood? When we have a nested function, in order to keep track of the functions, that means where it has to resume after returning from the function, they are going to make use of the stack. What TC stands for? Respond Modi, why?
Program counter, ma'am.
What it contains? It contains address of the next instruction which has to be fetched from the memory for execution. So what do you mean by this sentence? It contains address of the next instruction which has to be fetched from the memory location. So assume that we have the memory 100, starting memory location, next memory is 104, next memory location is 108. Okay, so now assume that in the instruction, in the memory location 100, we have add R1. Okay, in the memory location 104, we have multiply R2. So now assume that add R1 is getting executed. Okay, assume add R1 is getting executed. So what will be the contents of the program counter? Which instruction has to be fetched next? Multiplication R2. This instruction has to be fetched so that it will get executed. So where exactly this multiplication R2 is present? At the memory location 104, we are assuming. Okay, that means now the program, if the add R1 instruction is getting executed, the program counter will be having the address of this multiplication R2, which is at the memory location 104. That means the program counter will be having the address of this next instruction, MUL R2, that is nothing but 104. So now assume that MUL R2 is getting executed. So the program counter will be having the address of the next instruction, which is at the memory location 108. Assume here you have some division like that. Understood? Always the program counter will be consisting of address of the next instruction which has to be executed. Address, not the instruction. It contains address of the next instruction which has to be executed next. Is it clear? Then this status register SW, it is also called as SW, status word. It contains variety of condition codes that will be present in the status register. So in the last class also I have explained there are so many types of condition codes. What do you mean by condition codes here is, so we have a built-in condition code that is nothing but O. O stands for overflow. So overflow of this bit will be set to 1 whenever there is a overflow when you are performing addition of the integers. Okay. So or whenever you are taking an array and you are trying to insert an array element which is beyond the size. At that time this overflow will be set to 1. So this is a condition code. Where exactly this condition code it is present in? It is present in status word. It is a register. Okay, this status word. It contains variety of information. What it contains variety of information in the sense? It contains the condition codes. Condition codes in the sense we have bits like O bit, we have Z bit. So this Z bit will be set to 1 whenever answer of the result is this Z bit will be set to 1 when the answer is 0. That means you have performed addition or you have performed multiplication or division. Any operation you have performed, but the result is 0. So at that time this Z bit will be set to 1. Like that, we have a O. It is also a condition code. So this will be set to 1 whenever there is a overflow. So like that, this Z, O, all these are called as condition codes. So where exactly this is present Z, O in a status word. Is it clear?
Yes, ma'am.
Okay. ಇದೆಲ್ಲ C1 ಅಲ್ಲಿ ಓದಿದ್ದೀರಾ actually. I don't know how many of you are remembering. Same thing you are studying by using SIC machine. Next, data format. So this SIC machine is going to use 24-bit numbers, 24-bit in order to represent the binary numbers. That means when we have integers, we know that integers are represented by using 2's complement, right? How the integers are represented in the system? Are you going to use sign and magnitude representation? Or you are going to use 1's complement, or you are going to use 2's complement? Which format is used for representing the numbers? 1's complement, 2's complement. Which format is used for representing the integers?
2's complement.
2's complement, right? Here also same thing. Now stay we are using the system. Any number we represent, internally it is converted into 2's complement only. We cannot use sign and magnitude and we cannot use 1's complement. ಏನಕ್ಕೆ ಅಂದ್ರೆ negative numbers vary ಆಗುತ್ತೆ. You will not get the correct answer. So in the SIC machine, how many bits are used for representing the integer numbers? 24 bit. ಏನಕ್ಕೆ ಇದು 24 bit? Why not 32, something like that? What is the size of the memory they are using here? What is the size of each word? It is 3 consecutive bytes, right? So 24 bits baratte. So here also same thing. So integer numbers are represented by using 24 bit. Okay, you know that integer numbers are represented by using the 2's complement. Okay, this 2's complement is also used for representing the negative numbers. I hope you people know how to write a given integer number in a binary. Okay, now ಮತ್ತೆ 2's complement number. When we want to take a negative number, you have to take the 2's complement of that binary number. Okay. Then how do we store integer? How do we store characters here is by using the ASCII code, 8-bit ASCII code. ಇದೆಲ್ಲ ನೆನಪಿದೆ. I hope you people know. You have an ASCII code for all the letters. Here this SIC machine is not supporting floating point value. That means there is no hardware to perform operations on floating point. It supports only the integers. Okay, you know that positive integer number is represented as just binary, right? But once after, suppose if there is a negative number, ಏನು ಮಾಡಬೇಕು? You have to convert that number into the binary. Again, you have to take the 2's complement of that number. So characters are represented by using the 8-bit ASCII code, and this SIC machine is not supporting floating point values. Is it clear?
Yes, ma'am.
Write down. data format. Then is the instruction format. Then is the instruction format. So whenever we have this assembler here, when we have this instruction, what is the format of the instruction here is opcode. See, from now onwards you have to understand correctly. Okay, what is the instruction format here is, in higher level language you will write no, C is equals to A plus B. Okay, that plus is indicating that it is an addition operation, right? So, but in assembly level language, we are going to use mnemonics. Okay, you are going to use mnemonics. That mnemonic is going to become the opcode. So, I will write here. You can observe. Opcode I will write like this. Add. Okay, now what is the instruction format here? It is opcode. So, how many bits are used for representing the opcode? 8 bits. Okay, and 15 bits are used for representing the memory location. Assume that, sorry, it is 15 bits are used for specifying the address. Address in the sense here, assume that I have like this, location, comma, location. Okay, and really what do you mean by location 1 and 2 here is, so what do you mean by location here is, assume that, and then instead of taking the numbers in order to represent the address, we are taking the alphabets. LOC1, that is address of the first location we can consider as LOC1. Address of the next memory location you can consider as LOC2. Andre, this is the memory location, the first memory location. Instead of taking the address of that memory location as some integer, we are taking it as LOC1. So how many bits are used for representing this address LOC1 according to the instruction format? Yes,
24 bits.
24 bits alla, address, only the address part.
15
Address
bits.
part is 15 bits. That means 15 bits will be specified for address, 8 bits will be specified for opcode. What is this X here? What it is indicating? ಕೆಳಗಡೆ ಇದೆ ನೋಡಿ. X you have studied now,
Index.
X register, index register. Andre, for the X register index, X will be specifying index addressing mode. So, and how many bits are used for representing X here is 1. So, totally how many bits are there in the instruction?
24.
So, the 24-bit format is used for specifying the instruction in the SIC machine. Okay, you will understand what are the opcodes we have and how do you specify address and when this X bit will be considered. Okay. Take down instruction format. You write this one. Opcode. Write the format opcode X address. You should know the bits. For opcode it is 8 bits and for X it is 1 bit and for the address remaining 15 bits. Totally 24. Okay. For this addressing mode, I will explain later. Then we'll go for instructions what we have in the SIC machine. These are the instructions you should remember. So I will explain the instructions what we have in the SIC machine. So in the SIC machine, to perform arithmetic operations, we have instructions like ADD. So this ADD is going to become the opcode, or it is going to become the mnemonic. That means if I want to specify instruction add, if I want to perform addition operation, then what is the instruction we have to use? ADD, add. Then if you want to specify, if you want to perform subtraction, then you have to use the instruction SUB, subtraction. Okay. Then if you want to perform multiplication, then you have to use MUL, multiplication. Then for division, it is DIV. So arithmetic operations are performed by using the mnemonics or the opcodes as, and by using the mnemonic as add, subtract, multiplication and division. Write down integer arithmetic operations. Just you write down the list. Okay, right? Integer operations, integer arithmetic operations, add, subtraction, multiplication and division. Only three letters you need to use. This instruction. 3 letters: add, subtraction, multiplication and division. Now we have this LDA. What do you mean by LDA here? What is LDA? What is LD stands for?
Load.
Load.
What it will do? What it will do?
Load accumulate.
Load into, if I specify load LDA, if I specify load into accumulator. From where it will load? Which contents will be loaded onto the accumulator? From the memory. You see, whenever we have the processor, so the processor is connected to memory, right? 1 second, I will show you that. You look into this diagram. Okay, on the right hand side I'm having. So this is the processor we have. We have the memory. Memory in the sense it is RAM here. So within the processor we have a registers R0, R1 like that. And I told you now you are having a PC. It consists of address of the next instruction which has to be executed. Like that, within the processor you will be having a accumulator also. You are having accumulator, the register, index register, like that. Within the processor we have the accumulator, we have index register. So many special purpose registers are there. Okay, when we say LD instruction, it's going to load the contents of the memory location onto the processor. Okay, when we say LD instruction, it is going to load the contents of the memory onto the processor. Suppose if I say LDA, what it is going to do? It is going to load the contents of the memory location onto the register, onto the accumulator. That means LD means storing the contents of the memory location onto the processor. Suppose if I say LDA, the contents of the memory location will be stored onto the accumulator. Is it clear? And then you are bringing the contents of the main memory to the processor. Is it clear?
Spam.
Yes, ma'am.
What is ST stands for? LD means load. ST means
Store.
store means from where to where the data will be stored. It is reversed to load. What the load will do? It's going to load the contents of the memory location to the processor. Then what is ST? What is ST? It's going to load the store. It is going to store the contents of the registers to the memory. Suppose if I specify STA, it's going to load the contents what we have in the accumulator to the memory location. That memory location you are going to specify where exactly the data has to be loaded. Okay. Suppose if I specify STA, Okay, it's going to store the contents of the accumulator to some memory location or to memory. Understood? What is LD and what is ST? Understood?
I would try opening now, it is not opening.
If I specify LD X, what will happen? Yes, LD
Load
X.
index.
Load from the memory location onto the register X. Suppose if I specify STX, storing from the contents of, it is going to store the contents of the X register to the memory location. ಮಾಡಬೇಕು ಆಮೇಲೆ ಮಾಡ್ತೀವಿ ಸರ್, ಈಗ ಮಾಡ್ತೀವಿ, ನಾನು ಓಕೆ. ಅಂಡರ್ಸ್ಟುಡ್? So these are load and store operations. I mean, these are also called as memory operations. Load and store. So this comparison I will explain next. Next, we have conditional jump instructions. What do you mean by conditional jump instructions? What are the instructions we have? JLT, JEQ. What do you mean by JLT? Jump instructions. J stands for jump. LT stands for jump on less than. That means if I specify, new loop use ಮಾಡ್ತೀರಾ ಅಲ್ವಾ? Assume that in C language you will specify if A is less than B. You will give a loop. I mean, you will give a label. Go to P1. P1 you are going to define somewhere. Okay, na? Andre ಇಲ್ಲಿ ಏನಿದೆ? It is less. If the A is less than B, you go to the P1. Right? So now if I want to use this jump less than symbol, then what is the instruction I have to use? I have to use something called as JLT. J stands for jump and LT stands for jump on less than. That means I'm using a conditional jump instructions or conditional branching instructions. So ನೀವು ಇದ್ರಲ್ಲಿ ಬರೀತಿರಲ್ಲ C language, if A is less than B, you will execute some instructions or you will go to some label. Here if I want to specify jump, conditional jump, if I want to use conditional jump operations, then I have to make use of JLT. Jump on less than. Now what you do means you understand the instructions what we have. Once you write a simple programs, you will understand. JLT stands for jump on less than. What is JEQ? If I give like this, if A is equals to B, I am comparing equality. Then at that time we can use JEQ. What is JGT?
Greater than.
Jump on greater than. Yeah. So when we want to use conditional jump operations, at that time we have to use the instruction JLT or JEQ or JGT, stands for jump greater than. So based on these operations, these condition codes what we have, those will be set. I will explain what are the condition codes we have. I have explained that there is a Z condition code and the overflow. Like that we have so many. So based on the operation, those condition codes will be set. Okay. Next, for calling a function, how do we call a function? Assume that we have a main function. Main function is calling f1. Andre ee tara brace haki you will write. That means now this main function is calling f1. But ಇಲ್ಲಿ ಯಾವ instruction use ಮಾಡ್ತಾರೆ for calling the function? Yes. Next, what we have? Subroutine linkage. What are the instructions we have? JSub. JSub stands for J means jump. SUB stands for jump to
Jump
subroutine.
subroutine.
Jump subroutine. R sub means return subroutine. Return from the subroutine. Okay. So this jump, Andre, when we want to call a function, say here we have a main function is calling f1. Andre, if we want to call a function, we have to use jsub instruction. When we use a jsub, we have to use rsub also. So what will happen when this jsub function is called? It is going to place the return address in the linkage register L. I told you what do you mean by linkage register. Okay, so when this JSub instruction is called, it is going to store the return address onto the linkage register L. And this, when we use this rsub instruction, what it is going to do? It will be jumping, the control will be jumping to the address which is specified in the linkage register L. Okay, I'm repeating. JSub, jump to subroutine. What will happen when JSub is called, JSub instruction is executed? It's going to store the return address onto the linkage register. Okay. So each and every JSub will be having a corresponding RSub instruction. So when this RSub instruction is executed, we say that the control will be returned to the address or it will be going to the instruction or the address which is specified in the register L or it is specified in the linkage register.